So, today, as you can see from the title, I'm going to talk about seismic and acoustic detections and localization of an iceberg collapse in Antarctica. And the reason I decided to put this picture with all these cute penguins is because they're the local residents of Atka Bay, which is where we conducted the study. And this picture was taken by my colleague, Dan Zitterbart, who studies them. And actually all this research interest started a couple of years ago after a conversation Dan and I had where he was telling me about the importance of ice conditions to the penguins. And he asked me if we could use seismic and acoustic recordings to monitor the ice conditions. And this question led me to this very deep rabbit hole of seismoacoustics in the context of ice dynamics. So this is the grand plan for today. We're going to talk a little bit about the introduction and motivation. Then we'll talk about observations. We're going to then put everything together, synthesize all the observations, and we'll see what we can learn by combining different seismic and acoustic recordings. Then we'll talk a little bit about localization and finish with some conclusions. So I asked ChatGPT, what is seismoacoustics? And this is what it said. Seismoacoustics is an interdisciplinary field that studies how elastic waves or seismic waves and acoustic waves interact and propagate through coupled environments such as the solid earth, ocean, ice, and atmosphere. And it draws on principles from seismology, acoustics, and fluid dynamics, and is useful for understanding how different media influence wave behavior and how wave signals can be used to study natural phenomena. And I must say that this is a pretty good definition. I will add to it and say that integrating observations from different media provides us a more comprehensive understanding of the underlying physical phenomena and processes. And in the context of polar seismoacoustics, because this is what we're interested in ice dynamics, we deal with a coupled system that consists of the solid earth or seabed and ocean and ice and atmosphere, and we have elastic and seismic waves and acoustic waves that can propagate in all different media. For example, we can have seismic waves propagating in ice shelves, and seismic waves can radiate energy to the atmosphere and to the water that then propagates as acoustic waves. And these acoustic waves can then couple to the seabed and propagate as seismic waves, and these seismic waves can radiate energy back into the ocean. So there's a lot of interactions between the different waves and the different media. And there are various sources that can excite these waves, specifically in the context of in polar regions. We have ocean tides and ocean waves and drifting icebergs and ice-ice interaction. Think of icebergs colliding into each other. We have ice cracking and calving, and I put ocean currents in the question mark because this is not clear yet, but temperature changes, and there are probably other sources that I forgot. And just to highlight two examples that we're actively working on, this figure shows the spectrogram. That is the frequency, how the frequency contact changes over a week of a seismometer that is deployed on an ice shelf in Antarctica. And what you see is this periodic high intensity or high seismic energy that shows as the yellow stripes. And yes, and these are perfectly aligned with ocean tides that are shown by the white curve. And so these are the temporal dependence of this background seismicity, but there is also a special dependency that I'm not going to talk about. Another example is we studied the interaction of ocean waves and landfast ice. So here, for example, we deployed 1.5 kilometers of fiber optic cable in Alaska on the landfast ice in order to measure ocean wave and ice interaction. And on the right, you can see two examples of the recordings. In the vertical axis in both figures show distance along the cable, and the horizontal axis shows time. And you can see these clear wavefronts propagating along the cable. So this is basically very similar, same technology that Tsachi here is using for earthquake monitoring, but on sea ice. And I think just as an example, show how we put it there. Basically, it's quite exhausting. For a very long day, we just drag the spool of the cable with a snowmobile with this device that makes a groove into the ice, and we had to walk behind it and make sure that the cable is placed inside the groove, and we had to cover it just to ensure that the coupling is best as possible. It was quite tiring.
What's the difference between the two panels?
Just two different cross sections. So this one here is the last part, this leg, and this section here, I think it's around this part.
So do the waves really propagate in different
Yes,
ways?
so these are ocean waves that once they interact with the landfast ice, so this ice is about 1 meter thick, and it just causes this flexural gravity waves that propagate inside the ice or through the ice. And actually using these kind of measurements and calculating the dispersion relation, we can obtain the properties of the ice. Yes, using the phase speeds, yeah. Okay, so there are many different phenomena, natural phenomena that can excite these waves. And as I mentioned, what we want to do is to use seismoacoustics to study these different ice dynamics. And to do that, we first need to characterize the distinct signature of the different phenomena. First of all, we need to figure out if there are distinct signatures for different phenomena, and if there are, it will allow us to then quantify their effect. And as I mentioned, we have projects both in both poles, in Antarctica and in the Arctic. And today we're going to focus on one specific phenomena or source. And this is our study area in western Antarctica. We can zoom in a little bit more. So we're talking about Atka Bay, that is right here. There is the Ekstrom ice shelf, where the Neumayer station number 3 is at. This is a German research station. And in this figure, everything that is in blue is the ocean. Everything in green is a floating ice shelf. And everything in brown is land-covered ice. Just to give you a little bit of context of a bit more input on the bathymetry and the geometry of the region, this figure shows the water depth or the bathymetry below the ice shelf. So actually, this area here, this is the Atka Bay, which is on average about 150 meters deep. And you can see how in different areas underneath the Ekstrom ice shelf, the water depth can range between a few hundred meters to almost a kilometer. And this figure here shows different cross sections. And you can see that roughly the ice shelf is about area between 200 or 300 meters thick. And as we get closer to the grounding line, the thickness of the ice shelf is increasing. It can be almost a kilometer. And every winter, Atka Bay freezes. So obviously we cannot see it here because it's covered in ice, but it's around here. This image is from the satellite image from December 30th. And you can see that.
Is that summer?
What?
That is the summer.
Yes, that's the beginning of the summer. So it freezes over winter, and the ice stays until the beginning of the summer. And you can see that very quickly, within less than, or about a month, the bay, the ice disappears, it melts, it breaks, and we get an ice-free bay. And this process happens very, very quickly. And so today we're going to talk about the iceberg collapse, which happened on January 12, 2022. And the location of the iceberg is marked by this black circle, and it's obviously very hard to see it. But here we can zoom in a little bit more. So we can start to see the iceberg, which looks very small compared to everything around it. Just for example, this ice floe here, this part is roughly 4 or 5 kilometers long. And now when we zoom in a little bit more, we can see that it has a rough triangular shape where each side measures about 300 meters. So although it looks very small, it's actually a pretty big chunk of ice. And especially think about the water depth there, which is about 150 meters, and that it's quite a big. It's pretty big relative to the water depth. And I think that will be important for later. Okay, so the collapse itself is not a unique process. It probably happened a million times in the past and will happen many, many more. But what's unique in this specific case study is that this collapse generated seismic waves propagating the seabed and ice, hydroacoustic waves, which are sound waves that propagate in the ocean, and infrasound, which is low-frequency sound that propagates in the atmosphere. And all these waves were measured by this local seismic and acoustic network. So here, Palaoa, that's a hydrophone station that is deployed through the ice shelf in a depth of 150 meters. IES-27, that's an infrasound array. So this is an array of atmospheric microphones that record low-frequency sound, and it's deployed on the ice shelf. Next to it, there's VNA-1, that's a 3-component seismometer. And at the bottom, we have VNA, that's a 15-element seismic array of vertical component seismometers. And VNA-2, it's another 3-component seismometer. And the other unique part of this study is that there's also a ground truth verification of the event. And that was key for this study. So it was observed by my colleagues that were working on the sea ice when the iceberg collapsed. They were quite close to it. And the reason that it was a key element of this study is that this environment is very dynamic. The ice is always moving and changing, and there are seismic and acoustic waves measured all the time. So we needed to know what we were looking for, and we needed to know what we were looking for, and also in order to associate and combine the measurements from the different instruments and verify that know that they're all coming from the same source. And as you'll see later, based on these observations, we could determine that the collapse occurred also in at least 3 stages, separated by 16 seconds and then 8 seconds. And since we're going to talk a little bit about seismic and acoustic array processing. I don't know how familiar you are with it. So I'm just going to quickly go over the concepts and the advantages of using arrays. So the advantage of using arrays over a single sensor is that it allows us to obtain the wave parameters. That means that, for example, if we have a plane wave, this is a planar array, so it's deployed on the land. If we have a wave propagating from east to west, based on the time difference of the recordings between the different stations, we can use array processing techniques and determine that the direction from which the wave arrived at the array, which we call the direction of arrivals or the back azimuth, it points usually towards the source. One thing to keep in mind is that for atmospheric acoustics, if we have winds, depending on the wind field, they can shift the resolved azimuth that we calculate. And similarly, in seismology, local geology can also shift a little bit the resolved azimuth and cause some deviations with respect to the source location. All right, so let's go over the observations and see what kind of waves we recorded. I'm going to start with the hydrophone recording. That's the Paloa. Okay, so as I mentioned, the hydrophone is deployed at a depth of 150 meters. It records at 96 kilohertz. And this figure shows at the bottom the recorded waveforms, and on the top frame shows the spectrogram, which is how the frequency content changes over time. We labeled here 4 signals of interest, where each number corresponds to a potential stage or collapse stage. And here, instead of just looking at them, I would like to play you these recordings because it's pretty cool. So this was the first stage of the collapse. You could hear that it sounds like this rumbling thunder. This was the second stage. You could hear the difference between the two. This was much more impulsive. You can also see it's very short in time. That was the third stage. And that was the fourth signal. Yes.
In the quiet zones between the events, why there are strikes horizontally of
These ones.
why some frequencies in the background noise are more have higher amplitude than the others?
I'm not sure what this strike is.
Even the yellow, green, yellowish around the...
Yes, I'm not sure. It might have to do with some local dynamics. I mean, these stripes. Yeah, I'm not sure what's why they're there. Can anyone guess what's this kind of siren-like sounds in the background? So these are Ross seals. So this is very weird. It sounds like outer space sound. All right. So this is pretty much it for now. With respect to the hydrophone recording, we saw 4 potential signals of interest. They have different characteristics. The first one sound more like a long, this rumbling thunder, and the other ones were a bit more impulsive. Third one, you can see it has a lower amplitude and slightly different maybe frequency content. It looks different than the other ones, and we'll come back to it later. All right, so now we're gonna move on and look at the seismic recordings, and we're gonna start with the VNA. That's the 15-element seismic array. Right, so this is these are the results of array processing. There's a lot of information there, so I'm going to go through it slowly, and feel free to stop me if you have a question. So the top frame shows the spectrogram of the signals. The second frame shows the recorded waveforms. Also here they're labeled in different numbers. The third one shows the resolved azimuth or back azimuth, where the blue line in the middle marks the azimuth towards the iceberg. Maybe I didn't mention it earlier, but since we had ground truth observations of the iceberg collapse, we knew where it was, so we knew what we were looking for. This is how we could verify the azimuth. And the fourth panel in the bottom shows the apparent velocity. This is the apparent velocity is the phase speed, or the velocity that the wave sweeps through the arrays, and it can be used as an indicator for the inclination angle, meaning how steep the wave arrived at our stations. So we're going to start with signal 1A. That's the first observed seismic signal. Its back azimuth deviates about between 8 to 9 degrees from the true azimuth towards the source, and it has apparent velocities of about around 6.2 or 6.5 kilometers per second. And we interpret this wave as a fast propagating head wave. This wave probably propagated along the seabed bedrock interface. This is why it has higher propagation velocities, and this is why it arrives with this kind of steep angle at the seismic array. Now, next signal that we see on the array is signal 1C. There is also signal 1B that we don't measure. We don't see it on the array, but we'll look at it later. Signal 1C has back azimuth values that deviates between maybe half to 1 degree from the true azimuth towards the iceberg, and phase velocities or apparent velocities of around 3,000 meters per second. Based on some of these characteristics, but also particle motion analysis that I'll show you later, we could determine that this is a surface Rayleigh wave. After signal 1C, we see this very strange behavior in changing in azimuth and the apparent velocity. We're not sure exactly how to explain these observations. Our hypothesis is that this is probably some very unique multipath propagation and reflection and refraction from different, due to geological probably structure and maybe the ice shelf structure, but we cannot explain this very systematic change in back azimuth. After that, we have signal number 2, also with azimuth deviating between half a degree to 1 degree from the azimuth towards the iceberg. Also here, this signal has phase velocities, apparent velocities between 2,800 to 3,200 meters per second. This is also a surface Rayleigh wave. And then we have signal number 3, which has lower amplitudes, also kind of points towards the iceberg, but has a different small deviation from the iceberg azimuth, and higher apparent velocities. This signal probably also corresponds to a third collapse stage. And the reason that we know that all these signals are associated with these other signals that we saw in the hydrophone recordings, is that the time difference, the propagation time of all these signals between signal 1 in the hydrophones and signal 1 in the seismic recordings, and the different propagation time between signal 2 in the hydrophone and signal 2 in the seismic data, same goes for signal 3, are all consistent, meaning that they propagated through the same or similar propagation path and propagation distances. All right, as you can see, there are no evidence for signal number 4 that we saw in the hydrophone recordings. We'll talk about it later. At the center of the seismic array, there is. Okay.
You said that there are 15 sensors there in VNA 1 and 2.
Yes, VNA is a
so
15.
Where are the 15? I'm missing the 15 arrays.
No, so the 15 elements comprise the arrays consists of 15 elements. So we use all 15 sensors as
So
one
the
array.
distances between them give you the
Yes,
travel time.
exactly. Based on the distance between them, we can calculate the azimuth and the apparent velocity.
They
Yes.
have the same depth.
Yes. Based on their locations, it's a very simple calculation. As I mentioned, in the center of the array, there is a 3-component seismometer, which allows to perform a particle motion analysis. So, for that we had signal 1A that I'm not showing here, but it's this kind of small waveform, around 25, 28 seconds. Then there is signal 1B that we didn't see in the array observations. The waveforms that I plotted at the top here are the red, green, and blue correspond to the different axes of the seismometer. So we have in red the vertical axis, in green the radial axis, and in blue the transverse axis. And you can see that the signal shows up only in the radial direction. So both radial and transverse are the horizontal directions. If you look at the top left frame here, which shows the particle motion in the transverse versus radial components, we see this back and forth movement along the radial direction. And this is a characteristic of a horizontally propagating P wave that moves back and forth along one of the elastic layers. And the reason that we don't measure it in the seismic array is that it propagates only in the horizontal direction. Since the seismic array records only vertical motions, it couldn't record this wave. This signal is followed by signal 1C, as I mentioned earlier, that was a seismic surface Rayleigh wave. And the indication for it is shown in the center bottom frame. Here we plotted the vertical versus radial components of signal 1C, where it shows this typical retrograde motion that is a vertical characteristics of surface Rayleigh waves. Now, moving on to the other 3-component seismometer, VNA1, maybe just for a reminder. So the array, seismic array, and VNA2 that we talked about earlier are deployed on land or ice-covered land. VNA1 is deployed on the floating part of the ice shelf. And here, again, I plot at the top, we have the in red, green, and blue, the vertical, radial, and transverse components. And we highlight 2 signals here, but I think what's really important is, or interesting, is that on this seismometer, we only record surface Rayleigh waves. We don't see any evidence for body waves. And If we'll have time, we're going to talk about it later, but it has to do with the geometry of the problem. So here we have an ice shelf. Underneath it, we have a water layer of about 200 or 300 meters, and then the seabed. All right, and so now in this figure, we plot the azimuth, the result azimuth from the seismic array. The black arrow corresponds to the azimuth of the first Rayleigh wave that we detected, and the purple ones correspond to the mean and standard deviation of all the calculated azimuths. Now we can move on to our last observations from IES 27. That's the infrasound array. And this is a microphone array that is deployed on the ice shelf, and it records low-frequency atmospheric sound waves. Again, the top frame shows the frequency content of the signal. The second one shows the waveform. You can see that it's very prominent waveform. It lasts about 8 seconds. And the back azimuth is perfectly aligned. Again, the blue line corresponds to the azimuth from the array to the iceberg. And you see that the result azimuths are perfectly aligned in this direction. And in the bottom, we show the apparent velocity, and you can see that these values start with about 323 meters per second, which is typical sound speed in the atmosphere. And you can see that after about 5 seconds, this value increases. So we're not surprised by the accurate back azimuth that points exactly towards the source. Actually, it's infrasound azimuthal information is known to be quite stable and reliable compared to seismic azimuthal information. And the interesting part here is actually this trend in the apparent velocities that are slowly increasing. I'm not going to talk much about it, but what I do want to say is that atmospheric models, so we wanted to know why do we see this trend. So we looked for atmospheric conditions using ECMWF. We got an ensemble of all possible states of the atmosphere, and none of them can explain these observations, which led us to conclude that this trend that we see here is due to some small-scale atmospheric inhomogeneities that are not captured by atmospheric models. And there are some people that actually use...
Warming by the first arrival of the wave.
So this, in the atmosphere, acoustic propagation depends on temperature and winds. And if the models don't capture the temperature and wind fields properly, we cannot explain it. And there are some people that actually use this kind of observations to invert for the temperature and wind fields, especially for these small-scale structures that are not captured by atmospheric models. All right, and now we also plot here the back azimuth, the azimuth from the infrasound array. And just by looking at where these azimuths cross, you can see that it's very close to the location of the iceberg. Are we good on time?
Yeah.
All right. So now let's try to put everything together and see what we can learn from these observations on the sequence of the breaking sequence, the mechanism, and the propagation. We talked about different propagation paths. So we propose two potential excitation mechanisms. First one is that the collapse generated a pressure disturbance or pressure wave in the water that then coupled to the seabed and excited the seismic waves that propagate outward towards the different seismic station. The second mechanism is that the iceberg collapsed, and due to its size and relatively shallow water depth, it exerted a force on the seabed that excited the observed seismic waves. And these mechanisms are not mutually exclusive, and they may function either independently or jointly. And based on the observations and based on the data that we have, we cannot determine which one actually happened.
So the difference between them is whether the water is involved in it or not?
The difference is whether the iceberg, the difference is how the seismic waves were generated. In the second one, it was heat,
So the
excited
iceberg
elastic
is
wave.
their body.
The first one is, imagine an acoustic wave propagating in a fluid through the water and then coupled. Yes. And based on the observations that we have, we cannot really determine whether it's one or the other. And we could probably only do that using some numerical simulations that will tell us whether one source or the other can generate a different observed seismic and acoustic wave field from one to another. All right. So, stage one, the first signal, was detected by all instruments. So we had hydrophone recordings, we had 3 distinct seismic waves with 1A, 1B, and 1C, and we had infrasound recordings. Based on the iceberg's location and the travel times and the acoustic propagation velocities in the water and in the atmosphere, we could estimate the initial breakup to be between these 2 different times. So this is 9 p.m., 12 minutes, between 15.8 and 16.2 seconds.
It's going forward a second.
Yes. Then, stages 2 and 3 were detected only by the hydrophone and seismic recordings. So we had here signal 2, different characteristics than signal 1, and we had the surface Rayleigh wave obtained, measured by the seismic array. The absence of infrasound signal suggested a collapse occurred underwater, and this hypothesis is also supported by the characteristics of these waves, of the hydroacoustic recordings. There's some work done on characterizing ice shelf calving that happens in the air or underwater, and they show different characteristics depending on where the ice shelf calve shows similar underwater acoustic characteristics, signal 2 or signal 1. So signal 1 happened in the air or partly in the air, and 2 happened completely underwater. And as I mentioned earlier, we don't have signal 4 was detected only by the hydrophone station. We don't have any evidence for it, not in the seismic data and not in the infrasound data, which leave this as a mystery, whether it's part of the collapse, is it a 4th collapse stage, or it's an unrelated event. We don't know. I'm gonna skip this one. We can talk about it more later. I quickly want to talk about how we can use these observations to determine the location of the iceberg. And that's important for us to know how much information we can have from these observations on the sources that generate them. And having ground truth information can help us estimate and the accuracy of different methods. So the first one is very simple. What we're going to do is look for the crossing of the azimuthal information from the infrasound array and the seismic array. And when we zoom in, so first if we look at the two black arrows, they cross about 150 meters north of the iceberg's location. And for the iceberg location, we use its center. And if we remember, given the size of the iceberg that measures about 300 meters long, this is a pretty good, accurate estimate of its location. If we use the seismic mean back azimuth, that is this purple line, and the infrasound information, it places the iceberg about maybe 300 or 400 meters southwest of its true location, which is also a pretty good estimate. Next thing we did was a Bayesian joint inversion based on the travel times that we measured. I'm not going to go, basically what we do, I'm not going to go over all the details, but the idea is to minimize the cost function and look for the potential locations that can best explain our observations. And the results are presented here. So these two figures show the posterior marginal probability density function of the source latitude and longitude. The contours are the PDFs in both figures, and the red contours correspond to the 90% confidence interval. On the left, we use only the observed propagation times. The true azimuth is marked by the red cross, and here the maximum PDF lies about almost a kilometer to the west of the iceberg location, and you can see that there is quite large uncertainty regarding to its location. What we did then is combining the observed times of the observed arrival times of the different signals and the azimuthal information from the different stations. And what we see is a significant improvement of the source location. Now, the maximum PDF is about 200 meters north of the iceberg location, and you can see how the uncertainty significantly reduced while still encompassing the iceberg's location. Which tells us that we can localize these different sources pretty accurately. So to conclude, basically we presented multi-volume observations and localization of an iceberg collapse. Based on these observations, we could determine that the collapse had at least 3 distinct stages, separated by 16 and 10 seconds. We saw the effect of the geology and ice shelf geometry on the different propagation path. And I think although the proposed interpretations of both the excitation mechanisms and propagation path are all grounded in observational evidence, there still remain hypotheses until we could perform a very detailed numerical modeling. And in looking or thinking about the bigger picture, as I mentioned in the beginning of this presentation, I said that we want to use seismo-acoustic measurements to study ice dynamics. And we want to be able to characterize the signature of the different sources, so we'll be able to distinguish between them. It still remains challenging to determine whether an iceberg collapse can be readily distinguished from other processes. This is the only, I think this is the only case study that had seismo-acoustic signature of an iceberg collapse from all 3 media. And some wave characteristics are similar to other phenomena, some are different. So we really need some more examples of this kind of events, but also others, so we could determine whether they are distinguishable or not. That's it. Thank you very much.
Okay, thank you. Questions?
Just a quick question. The iceberg itself is about, a few hundred meters
Yes.
or size, size. So when it breaks, presumably it breaks, begins in one of at a point along its perimeter.
Yeah.
You can't tell which one it is.
No.
So an error of 300 meters, an error, quote unquote,
Yeah.
is meaningless.
Yes. Yes, the uncertainty is very small. And moreover, I think usually we think about, it's easy to think about this process when, first for me, when I'm thinking about seismic or acoustic wave propagation, I'm thinking about point sources because they're so simple. But this is far from a point source, right? We don't know where it breaks and it rolls, does it collapse? I mean, there's so many processes there that we don't know exactly how the waves were generated and how exactly it broke. So it's quite a complicated source. Yeah.
So a little bit of an introduction. First of all, thank you for the talk. So the introduction is the way ice melts, right, is a big deal. Right? We don't really understand this. The Compton Polar model from 2014, how ice will melt under global warming, right? These big questions out there. The basic physics are still not constrained very well of how ice actually cracks and melts.
Yeah.
If you can take your method and pair that with an ice model, cracking ice model, you can try and ask what models are correct.
Yeah.
So is this something that you can try and do?
Yes.
And
Yes.
can you do this?
Not yet, but we're now, what we're doing now is trying to characterize different signals that we see because the data is so rich and there are many different potential sources. So for example, let's in both cases. Okay, let's start with this example where I talked about the ocean tides. This is just how this seismic field is measured in one point from a very big area. So imagine now that you have an ice shelf that is bending up and down. Right? It's a massive thing, and the signals come from everywhere. Now, where the signals are coming from? Are there specific locations that these signals are excited? We also see, I mean, it's all a bit hard to see, but there's this, in the times of the higher seismicity, we have these distinct blobs of energy that might indicate type of propagation that also tells us something about the properties of the ice itself. And so we're trying to understand where the signals are excited, why they're excited. When we look at this data with the arrays, we see some special dependency. And one of the reason when I wrote here ocean currents, because there's an hypothesis saying that some of these observations are due to both bending of the ice shelf up and down due to ocean tides, but also the rushing water along the water ice shelf interface or water intrusion into cracks. And also in this case, when we have measurements on landfast ice, in this specific area, the ocean tides are very minimal, but there are various different ocean waves that interact with the ice and potentially have different momentum transfer mechanisms that can lead to cracking and breaking and melting. And so these are things that we try to put together. Obviously, I'm not an expert in all of them, but I'm working with physical oceanographers and expert in ice research that we're trying to put all this information together.
Anyone else? Okay, but a short one, right?
You motivated your research by the effect of ice conditions on the penguins in the
Yes.
ecosystem. Can you actually link it to that?
Not yet, but the question, it's a really good question.
If it's a
Not
long
yet.
answer, we can do it afterwards.
Short answer is not yet, but we hope so. Yeah.
Okay, great. So thank you for an interesting talk.